program on emerging trends in biomedical engineering research for Healthcare 4.0, organized by the Department of Biomedical Engineering SSN in association with Center for Healthcare Technology and IEEE Signal Processing Society, Madras chapter. Dr. S. Praveen Kumar has 18 years of teaching and research experience, including 3 years of postdoctoral research experience. With Dr. Jan Beck, inventor of the high-speed video kymogram at Palak University, Czech Republic, in the field of biomedical signal and image processing. He received BE degree in Electronics and Instrumentation from Manomaniyam Sundaranar University. He completed MTech in Biomedical Engineering from Manipal Institute of Technology, Manipal. He earned his PhD from Jawaharlal Nehru Technological University, Hyderabad. His PhD involved developing signal processing and artificial neural network methods for automated epileptic detection from EEG signals. His postdoctoral work involved in developing signal and image processing and computer graphics methods to analyze the vocal fold disorders from the high-speed video kymographic images. His present research interests include biomedical signal and image processing, biomechanics, 3D modeling, medical instrumentation, medical data analytics, machine learning, artificial neural network, deep learning, and augmented and virtual reality. He has published several papers in reputed journals and international conferences and has also earned several awards and recognitions. In the 50-year history of the Voice Foundation, Dr. S. Praveen Kumar became the first person simultaneously awarded with the 2 prestigious research awards, Hamdan International Award and Sataloff Young Investigator Award by Voice Foundation, USA. We are so happy to have you here, sir. Welcome, sir. Over to you.
Okay, thanks for the nice introduction.
Thank you, sir.
So hope I'm audible and my screen is visible.
Yes, sir, you are.
Okay, so I hear some echo. All right. Okay, just confirm if I'm still audible.
Yes, sir, we can hear you, sir.
Okay, so okay, you can mute and then I can start my presentation.
Yes, sir.
Thank you. So the topic for today's discussion is augmented reality for healthcare applications. I'll start with my presentation. With the observation from Clay Bever, VP of VR Technologies in Google. In his keynote talk in the Google I/O in 2017, he mentioned that for the future of virtual reality, in broad terms for the immersive experience technologies, he has mentioned the future creators and consumers of technology. They will be imagining a new world, how the human experiences technology can take them to a new places, like what the eyes can see, where the eye can enable anyone to go anywhere or bring anything to the end user. So the person can be anywhere in the world. Whatever they are seeing, they can experience themselves by immersively being there at that place. So that type of immersive experience the technology is going to bring to the end user. And then they can control the presence in the environment and interact with the environment by using different input methods like voice gesture, voice control, or the motion gestures and other things. So this is the application of spatial computing in the future. So images, what we see so far, they offer a limited experience, like the unknown places. If the user want to see, they can simply go to the internet and then browse it, and to get the feel of it, they can get, for example, an image of a falls they haven't seen before. So that kind of visual experience they can have. But what about this immersive experience? Can we create 3D landscapes and project it on the head-mounted displays with the spatial audio features? This could offer an immersive experience, like they can hear the noise of the waterfalls falling, and then if they see Below, they can see the water is getting accumulated, and then above, if they look at that, they can feel the clouds moving, and then when they look back, they can see the rocks around, mountains around, left and right. They can see anywhere. So it's a 360-degree experience. It's like keeping the person inside that immersive experiment, immersive experience, and provide them that kind of feeling. So that's what we are aiming at. So this is possible through spatial computing. So we have many terms that will be introduced here in this lecture. Like we have a combination of real environment and virtual environment. If you go completely virtual, if you project all the digital assets as virtually in the virtual environment, that could be VR kind of experience we can have. Whereas if we are combining some digital assets over the real environment, then we can create an augmented reality. So the terms virtual and augmented reality put together, we can have a mixed reality experience. So now we have broadly introduced to those terminologies like VR, AR, mixed reality, and spatial computing. But how these developments are taking place nowadays? We know that the future of spatial computing, it depends on the open source knowledge what we have now, mostly open source. So we have different platforms, and users from different experience levels, they join hands together in terms of developing. So we have limited developments happening in the corporate world. Otherwise, all these technology developments in terms of virtual reality, augmented reality, and other spatial computing related technology, it is going mostly open source. So this allows collaboration, like you can have the experts, young and upcoming professionals, they work together across various disciplines to create this type of experience. So it has its own advantage. It allows anyone to collaborate with anyone and to develop that immersive sort of experiences and provide to the users. But at the same time, it has some limitations as well. Like we don't have any standards available for augmented and virtual reality. We have different toolkits, different types of environments, developing environments are available, but each differs from mostly there are uncommon things, like one platform follows certain routines, other platform follows some other routines, like that. So there is no standard yet available. So this makes anyone entering into the spatial computing domain, it becomes a little challenging because there is so much to learn. And there are so many new terminologies and set of technology paradigms that one has to experience. And these are all also constantly changing day by day. So it is kind of challenge that anyone wants to develop VR, AR based experiences. So when we develop some solutions in VR and AR, that is to take that solutions to the mainstream market, we have to have technology professionals across all roles, combining technical, creative storytellers and artists, business and marketing oriented professionals, hardware engineers, and full stack software application engineers, developers, designers, including industrial, computational, traditional, graphic designers, product designers, or user experience designers, UX, UI interface designers, data scientists, machine learning engineers, 2D and 3D artists developing graphics. It can include modelers, painters, architects, product managers, directors, and many more. So it's a combination of team with diverse experience. We need to make them collaborate to make one product out of the market. So anyone wants to enter this VR AR landscape, what to learn? Basically, we need to know the basic hardware and software methods available, particularly in optics, what are the different types of display devices and camera devices available, what we are modeling, the basics of optics and the mathematical background of it, and then perceptual engineering. So ultimately, we are creating an immersive experience to the user as if that person is in that virtual world. So when we do that, we need to know also the cognitive behavior of the user, what to show, what not to show, what should be the lag in the frame rate and the other things. So everything should go sync, the scene and if you are projecting something on the real environment, if you are projecting some virtual content on top of the real environment, then they should sync each other with they should sync perfectly well with each other. So these are all some challenges that we need to understand by studying the perceptual engineering. And then to make sure that everything works well, one has to know the computer vision based methods like tracking of the user head, eye orientations, and accordingly you have to project the images, and then some design aspects we need to know. And we also need to know the development best practices, especially how to design for the cross-platform. It's not just head-mounted displays we are aiming at. There could be variations in the head-mounted displays also, like you have HoloLens, you have Oculus, you have different other commercially available head-mounted displays. Also, you can also target not just head-mounted displays, how to create the AR environment on the mobile devices or desktop environments or gaming applications or different other things. So one application developed, how to make it universally the same application, can we deploy it for different other hardwares and systems platforms. So that is also one aspect we need to know. So just now we saw that given that standards are still being developing for many areas of spatial computing, the norms today, it's constantly evolving, and some routines, some technological methods, algorithms are followed some part of time, and then that quickly it's getting replaced by some other algorithms and some other methods. So we need to be in a constant track all these changes so that we will be up to date towards the development in that AR/VR domain. So what are the challenges? Apart from the challenges I just now described, the subject tends to be very dense and inaccessible. Most of the contents are not well written. So because it's an open source type of development is taking place, and we don't have any proper documented information available in the form of textbooks or some other contents. So users from different fields, they collaborate together with the professionals with the different backgrounds. They pick up some little bit of information about the hardware use and then computer vision algorithms or even design principles. So there are bits and pieces of information they have, and they collaborate with someone else. They also have some bits and pieces of information. So then this content is not yet maturely, it has not yet matured enough sufficiently. So subsequently, we create most of the time lower quality experiences and applications most of the time, which ultimately hurt the user experience. So the user experience in the commercial world is really important. How appealing the content we develop is really important. So there's a difference between the quality, the content which has high, rich quality, and the content which has not so good quality. So because of that, the bad application design could give bad experience to the user. Ultimately, they will get turned away from this technology. So this is development is much more challenging, because how to ensure that we develop a good application and that ultimately provides the user a very good experience of visualizing the virtual and augmented reality contents. For that, we need to understand how the humans traditionally interact with the computer based on you have the computer inputs. They are nowadays they are based on keyboards and mouse. But traditionally, we had different other ways of interacting using punch cards and different other ways. But now we have the standard, like we have the keyboard and the mouse. They are the key interface for that allows the user to interact with the computer. But when you go for spatial computing, when you develop this immersive experience, that input can be in different form. So when you think of developing some intuitive, innovative input devices, we need to make sure that these devices, whatever we are replacing, we are proposing, that should follow these 5 rules. Like it should be cheap, reliable, comfortable. It should have the software interface that readily makes use of the hardware controls, and then it should have an acceptable user error rate. So all these characteristics should be met before when we propose some new input for the spatial computing domain. So now let's look at what are the human computer interface modalities so far. We have, so it can be visual, it can show the graphics, text, UI interfaces, screens, animations, and it can track the poses and other things. So it can show like the interaction between the user and the human user and the computer can take place through auditory means, like the computer can give the auditory feedback like tones, and it can play some sound effects, or the user can talk with the computer through speech. So all these are possible. These are Kachi modalities. And using physical interfaces like just now we described, it can be hardware based buttons or haptic based real objects. These are all the available modalities where the human computer interface can take place. So let's see some of the key terms in the human computer interface. The modality is described as the channel of sensory input and output between the computer and human. Affordances are the attributes or characteristics of an object that define that object's potential uses, and the inputs are how we do the things, and how do we send the data to the computer. What do we want, that type of data, how do we send to the computer. Outputs are the perceivable reactions to an event, like the data sent from the computer, the data thrown back from the computer to us. So this is the loop which covers all these aspects. So affordance, like when you show some information, some content by the computer, when the computer shows some content to the user, this comes as a discovery phase, in which the user should find what they want to do, what they can do. So what to do with that object they are seeing on the screen. The second is the action phase, where the users do some action, like they decided like what type of action they want, they decided on that. And then the third is like after the user performs that action, the third phase is that computer gives a confirmation in terms of feedback, like it can be a reaction by the computer, like that confirms that it has received that information, and it can process or it can change its output in a way the user wants. So this is how the different levels interaction takes place from the human to the computer level. So this can fall in different domains, like the information flow exchange between the user and the computer can take place in different forms, different modalities. It can be physical, it can be audio based, or it can be visual based. So mostly our information exchange from the computer to us is in the visual form. Some of the times, like when you press some buttons or something, so that gives warning signs, that can be in audio form. So different levels of information exchange takes place in different form. The input is mostly in the physical form, like the keyboard press or mouse press. But we also have nowadays new modalities, like it's a traditional. These are the traditional way how what we described before, or the traditional ways how the user used to interact with the computer. Nowadays, with the advent of mobile phones and other sensor based computing tools, we have the different forms of interface interaction takes place between the computer and the user. Like for example, GPS sensing the user place, user location with the GPS signal, and based on that, some information can be exchanged between the computer and the user, and based on that, some information content that is related to that location can be delivered to the user. Also, we have the breath rate based inputs, voice tone, pitch and frequency based inputs, eye movements, pupil dilations. All these are different forms of inputs that can take place between the user and the computer. So these are the new modalities. So when we talk about the immersive experience, when we create the immersive experience, the current controllers for the immersive computing systems, they make use of conventional game controller based design. You can trace the new VR controllers design that's available nowadays. That can be traced back. The design can be traced back to the original joystick-based design traditionally in the classical games. The people used to have that. So this can be in a new avatar. They have that can be changed as per the applications and customized based on what the user wants to do. So only the placement of the sensor can be different, but usually we have these buttons in the joystick and then the touchpad. So this is what traditionally available before as well. So this is for mostly these are the controllers used for controlling the VR environment. But for augmented reality, we have different sets of inputs that we'll discuss later. So when we talk about the VR environment, the way of interacting within the virtual worlds that takes place through raycasting, the technology called raycasting. The raycasting is a set of interaction techniques that's used in the immersive environments for selection of the targets over a distance. It resembles kind of pointing with a laser pointer. So it allows the user to interact with the virtual object, like you are pointing with a laser gun. That ray is going and hitting the object. So once that object hits that, once this laser is hitting that object, the ray is hitting that object. The object gets selected, and the user can then interact with that object. So this is the way that interaction takes place. So this shows visual representation of that. So we have the VR controller, and from the VR controller, the ray when the person moves the VR controller, you can see the ray in the virtual scene. It gets moved, and it selects virtual object, and then the user can interact with that virtual object. So this is the kind of interaction which is possible with the raycasting method. And also, we have to have a basic tracking technology, which is the process of tracing the scene coordinates. So where the user position compared to the scene, that need to be tracked. And if the person is moving, accordingly, the projected object position need to change. So the content, virtual content, how it can be manipulated. It depends on what is the user position is, how that user is moving. So the user head position and body position need to be tracked in the real time. That is that's the key behind the tracking technologies. There are multiple ways of doing that. You have inside out versus outside in tracking methods. Inside out tracking, where the camera is attached to the user, and the camera position is tracked in the real time with respect to the user. Whereas in the outside in technology, we have the sensors placed, stationary bases are placed, and they kind of send some rays in the form of laser or ultrasound waves, and then it tracks the user position, the controller, where that user is placed in the environment that is getting tracked. So this is called outside in type of tracking. So in both ways, the user position with respect to the physical environment is tracked, and that is supposed to be reflected in the virtual environment. So that is the scenario we want to mimic in the virtual environment. So this is the case of tracking from the outside in, where the head position and the controller position, all of them are tracked by the beacons or the base stations that's mounted on the wall. So this is the example for the outside in tracking system. So Valve Index and HTC Pro headsets, they use these base stations. So they require at least 2 base stations installed in the room. So what do they do? These base stations serve as a reference point for a headset and the controllers. Each base stations, they emit the IR waves, and then they have this IR lasers getting emitted. And the controller has the multiple IR photo sensors. With that, we have a set of pulses getting emitted, and then that emitted pulses are received, and it is getting tracked throughout the room. So that once the controller, they detect the pulse, they start counting until one of the sensors is hit by the laser beam. And based on the laser's time of flight, the system then detects the position of the controller. So this is the operating principle of the outside-in tracking system. Whereas in case of the inside-out tracking system, we have the active IRs. This is utilized by Quest, ArcQuest Quest 2. Nowadays it's called as Meta Quest 2. They use this inside-out tracking system. The working principle is quite different from the one we saw before. Here, each control is inbuilt with the set of infrared LEDs located on the controller rings. So the camera located on the headset detects these IR LED lights and then continuously takes images of them. And then it uses the triangulation method to know where that controller position is with respect to the scene. How the Oculus tracking system controller looks like. You have the headset and then these controllers on the left side and right side. So you have for both hands 2 controllers, left controller and right controller. This is the controller, how it is getting tracked in the Oculus system using the inside-out technique. So when we compare these 2 tracking systems, the outside-in tracking systems are enhanced. They will provide the enhanced tracking accuracy and lightweight data transfer, whereas the inside-out tracking systems is cheaper to implement. You don't need to install separate base stations to track the controller. We don't have to that reduces the cost also. We don't spend much cost on installing these. So this is the hardware part, VR controller, how that buttons are placed in the VR controller. We have the joystick arrangements and buttons arrangement, and you have also trigger buttons on the sideways. So using this controller, the user can interact with the virtual object the way they want. So you can code information. We can attach the programs to the controller button press and then trigger press. If there are some triggering action is taking place, and what changes should occur in the virtual world, that can be programmed. We can attach the intended action through a set of programs. So that can be used for, like, once we develop the button press, and then we can attach some programs to that button press, and then how that virtual object should be interacted with the respect to the button press. We can use that to interact with the virtual world with the way we want. We can interact and make changes in that virtual objects. And also we can use the VR controllers. Depending on the applications, there are customized modifications possible with respect to the VR controller. For example, this is the customized controller for the shooting games applications. And also we can change the controller instead of the hardware-based controller. We can make our smartphones and other devices to interact with the virtual world. And also we can use our body parts that can be tracked, and then it can be used to interact with the virtual world. So you have the body tracking methods. The most widely used techniques are hand tracking, hand pose recognition, and eye tracking methods. In case of hand tracking, the user hands are tracked. Entire movement of the hand is mapped with the digital skeleton in forms of the nodes and links between them, and input inferences are made based on the movement or poses of the hand. This allows for natural movement, like how we naturally move our hands, that can be tracked. So these movements can include the picking up of some object, and dropping of some objects. So when we do that, this hand movement, the information can be tracked, and the action can be tracked, hand action can be tracked, and that can get replicated on the virtual world. So the hand tracking can be entirely computer vision based. How do we track the hands? It can be entirely computer vision based, or we can include some sensors attached to the hands in forms of gloves, or we can use other types of tracking systems to recognize the hand movement. The hand pose recognition is different from hand tracking. In case of hand pose recognition, it itself is a one specific field of research. Often it gets confused with the hand tracking. The computer has been trained in this case to recognize specific hand poses, like much like sign languages, and then it decodes that information and it understands that and produces the output. The intent of the user through hand pose is mapped when each hand pose is tied to specific events like grabbing, releasing, selecting, and other common actions. So accordingly, the changes should take place on the virtual objects. So on the positive side, the pose recognition can be less processor intensive compared to the hand tracking methods, because we have a limited set of actions that is encoded on the hand pose. So once the computer decodes only that much information, then it performs that action. But comparatively, hand tracking is little complex. So hand pose needs also less individual calibration than that's required for the hand tracking method. But externally, it can be tiring and confusing for the users. So what like they have to learn everything. What are the actions they are supposed to do? What are the poses they should make to perform one action? So that has to be properly taught about, and they need to remember all these things when they use hand pose based method to interact with the computer. So this needs a vast amount of learning and memorizing those contents. So these are other ways to interact with the computer, virtual world, like you can use the sensors mounted on the gloves, and the finger movement can be sensed, and that can be translated to the virtual based object. We can also customize the sensors designed based on the applications we want, like the points on the here, if you can see the points or of the hand position or the finger position is tracked, and then it can be used to play the keyboard. So it can recognize what's the finger position, and then accordingly it can create the key tones. Also now we have different other innovative controllers available in the market, like this ControlLabs wearable controller. Now it is acquired by Facebook. So this they use this technology, like the hand muscles movement can be tracked using a wearable device, and that can be used to control the virtual hand in the virtual world. Also, there are experiments like how to, like, it's not just manipulating the object, how to feel the object. So we have the haptic based feedback given in gloves. If the person is picking up a digital object, based on how solid that digital object is, the person can be given with some feedback, like force feedback, so that they can experience the weight of the object or whatever, however that object is designed. So now it is possible also to attach the VR controllers in the customized designs, like the baseball games. You have the baseball stick that is getting mounted with the VR controller, and the position of the VR controller in the physical world that can be tracked, and then it can make the game on the virtual world to track that, and then give a feedback to that virtual world, so that the game can be virtually played. Now the people have become innovative that they are using the VR controller to track the cat position of their pets, and that can be used to animate something on the virtual world. So these are all possible with spatial computing, whatever technology we have discussed so far, the controller and display, how that interaction between the physical and virtual world can take place. So these are part of spatial computing. So the spatial computing is, we can say that it is not locked in rectangles like computers, the 2D displays right now, what we have now, but it can flow freely in and through the world around us. Like you can place the sensors anywhere we want. Unlike this mobile computing and desktop computing before it. In other words, the spatial computing can use the space around us as a canvas for experiencing our digital space. When we design the digital content, when we make those digital content to interact with the physical world, what all the design consideration we should have? So this answer to this question it can be taken from the creative director of Google, T. Ogla. She has mentioned that in the TED talk. As a designer, I'm interested in how we access information in a way that feels natural. It should be simple and it should ultimately make us happy. So these are all the design statements. Whenever we design some digital contents and whenever we interact with those digital contents, when we interface those digital contents on the real world, it should be as natural as possible, it should be as simple as possible, and it should be as intuitive as possible to interact with those digital elements on screen. So ultimately, we are trying to humanize this digital experience, the way we interact with the digital world. So the dream of spatial computing is that we have to build a technology that can make the digital interaction as humanized as possible. For example, the input devices like mouse, keyboard, and even touchscreens intermediate our experiences in the scenario today. But with the spatial computing, we can use our voice, sight, touch in 3D, gestures, and other natural inputs to directly interact with the information. We no longer need to think and behave like a computer for it to understand us, because it will relate humanly to us. That's the dream of spatial computing. So spatial computing, it can happen anywhere we are, or on our wrist, or in our eyes, or in our ears, just like a car's GPS, and how to reach your road trip destination. It can identify what does the user want, and then based on that, it senses on in spatial domain, and based on that, it can alter the digital contents accordingly. So what are the techniques, technology, whatever we are building so far, what are we building this future like of this spatial computing, to whom we are building this? These are mainly for the younger generation. They call it Gen Z group, which comprises of 32% of global population of 7.7 billions. They are the avid users of this virtual mode of interaction, and then they are no longer, they believe in the binary identity. They believe they are experimenting, they are ready to experiment, and they are believing they can change their identity to any characters they want. So it's the example of AR mask. So it's not just a human face. You can change that face itself is to different forms. So that's a fluid identity. So that's the users are ready to experiment. So these users come from the younger population than the old or middle-aged populations. So we are building this technology mostly for the younger population to interact with. So the main goal of the spatial computing is to design for our senses. That's the goal of the perceptual engineering, not for the devices like the way we interact now. So when we design this, what are some of the problems that a sincere design can solve that no other medium can do? To answer this, we can consider one simple example using computer vision and AR-based technology that understands the sign language, which can that user poses can be recognized, and it can be translated into text, and then back again it can be produced as a sign language so that interaction that user can understand that. So that's one input way that the human-computer interface can take place. So there are Other frameworks also available for different other sensing modalities, like this is the framework which says what is the best method for different types of interactions for different types of sensors. Now we have this AR-based overlays, which allows to place the text on a 3D space. So this is example from the weird type, which it's an AR app that lets you paint with the text on the 3D environment, on a real environment. We can like there are tools available nowadays that can give the 2D or 3D assets, so that can be imported, and it can be overlaid on our real environment. Also, we can customize based on our requirement, so we can project what we want. So there are apps available which can allow us to make the interaction in the design the way the user wants. So with this background, let's introduce what is the AR technology. So the augmented reality is the improved version of reality. It overlays overlays and integrates the digital information on the real world, so that it enhances the real world view with the superimposed computer generated elements like images, videos, or 3D models. So this is the example of overlay, where when the surgeon performs the surgery, there are certain parts are not visible readily to the surgeon, to the surgeon's view. So these internal parts can be overlaid digitally on top of on the real scene, so that the surgeons can see that these spots are what's the depth of these spots are present. So for example, trachea or carotid artery. So these are the vital parts. So when they perform surgery, they are not supposed to damage these spots. So when we digitally overlay those information, the internal information, usually hidden information, then surgeon will know. So what is the depth that tool can be inserted without damaging those vital parts around. So this is the example for example application of augmented reality. But we know that to create the augmented reality, we have to overlay the digital content on top of the So we use the post estimation techniques to do that. For that, the algorithm should know what is the camera position, sensor position with respect to the physical scene. So we have the world coordinate and the camera coordinate, and based on that coordinates how the camera sees the world. Based on that, digital content should be overlaid. So if the camera is tilted or moved, accordingly the digital content also need to be changed. So that's a problem of registration and tracking. So to define AR, the AR, according to Asma, the author respected in this field, he defines the AR as the combination of real and virtual elements together. It should be interactive in real time. It's not that CGI, computer generated images or computer graphics. This, whatever the virtual content we are projecting on the real space, you should be able to interact with that real objects, with that virtual objects project on the real scene. And it should be registered in 3D. So these are also some definitions for VR, AR. So we create a spatial model of the real environment, and then we overlay the virtual content on top of the spatial domain, on top of this on physical space, using multiple algorithms. So for that, we have to take care of track the user's viewpoint, and we have to register the pose of the user, head pose, eye pose, and so on in the real world. Accordingly, we have to change the virtual overlay content. So this is an example for augmented reality use case. It is used in the advertisement in industry, like that's one of the use case in the advertisement industry. Now we can also use to uh, the content on the physical book we can enhance those content with the virtual artworks so that the user can have some other experience apart from the book content and the text-based contents. So you can overlay those digital information on top of it on the printed media. So this is another application of overlaying in the augmented reality based games. Or you can place the user itself in the virtual environment. That's another application. Or we can use it as a mapping application so that it recognizes the buildings and then it puts marking what the building is. It can be city landscaping, it can be used, or it can be used in the industrial maintenance to point out system and then to know what is the maintenance activity we should do with respect to the condition the system sees. So these are all some use cases. It can be widely. Nowadays we have the use cases widely in the advertising, archaeology, art, and education, games, GPS-based mapping, and industrial maintenance case. And also now people have started exploring on the potential application of AR in the surgery. Now we also have the application. Apart from this, we have it in sports. It's widely used to create the content on top of the physical space and to make it informative. So to distinguish between the different environments, so this is a real environment, and augmented reality is to fuse the digital content on top of the real environment. Whereas virtually, if you are creating everything in virtually, and then if that is seen as a 3D virtual environment, that is called as virtual reality. So these are all different terminologies as we saw before. And we also need to define what are the degrees of freedoms that one has to track with respect to the head position or camera position. So these are all like ideally we should track 6 degrees of freedom. It can be left, right, it can be forward, back, or up, down, and that is the positional changes. Also, we have the orientational changes that comes as yaw, roll, and pitches. So this example how visualization can take place, and that it can track the user camera view and the content it sees in 6 degrees of freedom, and accordingly it overlays the digital content on top of it. That's one of the applications of the tracking system. We can also use the trackers placed around to guide our virtual objects. So these are all the fiducial markers. They are placed around so that we can overlay our digital content on top of it according to the marker placement. A brief history, like the augmented reality is the term is first coined in 1992 by a Boeing engineer who used the head-mounted display to train to assist the workers in the Boeing airplane factory to display what is the wire bundles inside in the hidden space. So that this is how the term it came into existence from 1992. Before that, also people used to have the AR system. They were experimenting with the AR system. So 1968 was the first AR system, or the also first VR system created by Ivan Sutherland. So you can see the size of that VR display, head-mounted display. The weight is such it's so heavy that it has to suspend from the ceiling. Now, coming to the applications, you can think about many applications possible with the augmented reality and virtual reality, but very few have been made in the commercial stage. So because the 3D registration is still very challenging, and it is not yet clear how the human-computer interface should look like for this spatial computing space, because no standards have evolved yet. But at the same time, since this is not confining us, we have our research interest that can be established on the computer vision or augmented reality-based methods. So we can have the platforms or algorithms that can we can create algorithms and perfect algorithms which can superimpose the virtual information on the real world without flickering or without no occlusion, how to project it the way it is as natural as possible. And we have to also make it interactive in real time. Remember, the augmented reality is when you make that digital object interactable, then only it becomes augmented reality. Otherwise, it's simple CGI, computer-based graphics. So it should be also spatial, that registration should be done. So the object should be placed spatially. The virtual object should be placed spatially. So we need to perform the calibration and registration basic image processing operations to make sure that the virtual objects are properly anchored on the real environment. So this case, the registration, we are aiming at 6 DOF registration, 6 degrees of freedom, as we saw before. It's basically a computer vision based method. We can use cameras to estimate all these position and orientational aspects. Also, we can combine the data with the GPS and campus to guide us through. Rendering of this superimposing the virtual information, that explains the concept called rendering. So that comes from computer graphics and computer vision methods. And superimposing is the part of visualization method, how we display the information. So we can display it on the head-mounted display, or you can display it on a mobile phone or smartphone, or it can be monitor. So how we want to display, how do we want to superimpose and display the information together. And then interaction, finally, that interaction should come from the human-computer interfaces. So the research interest in this domain, it includes the computer vision-based methods like 3D localization, 3D tracking, models, gesture recognition, and computer graphics-based methods like real-time tracking, realism, how to create more natural scenes as possible, how to make this animation more naturally as possible, and visualization techniques, how to make it appealing to the user. And also the human-computer vision, human-computer interaction and user interfaces research interest include 3D interaction, how to make how to interact the object in 3D, how do we make the tangible interactions, how to make that object felt by the user. And we also have the hardware-based research methods, research possibilities like design of innovative displays, tracking systems, wearable and mobile computers. These are all the main areas where the research can take place. So this is one example for a 6D with the hardware-based techniques. So you have the computer vision-based method that registers also. It combines with the sensor data, GPS locations, to know what where the person is looking at. And this is the problem of occlusion. Without taking into natural environment, when we overlay something digitally, you can place your digital object like that. But when we handle the occlusion properly, see where that object should be properly placed. If there are any no objects in between, we have to recreate it so that you instead of directly overlaying on top of some impossible objects, can we keep it in between? So that is to know about what all the objects that occurs causing occlusions. So based on that, we need to decide which part on the digital display, digital element we have to hide. So that's another decision we have to make using our algorithms. And then we can render, like using the computer graphics based methods, we can render the shadows and reflections so that the digital object should look as natural as possible. So these are the key consideration we should have from the perceptual engineering point of view to properly overlay the digital contents on the real scene. So we need to realistically integrate the virtual and real content as much as possible. So creating the shadows and then blending with the scenes as much as possible. Otherwise, the object looks floating and it's not natural. So all these aspects should be taken care before placing any content, virtual content on top of the real content. So we also need to know like how much should we blur and how much should we, like when there's a motion when between the frame to frame, how much we should blur and how much should we leave it on the digital content so that it becomes a part of the real scene. So this is another example, how to take the camera perception into account and camera effects into account so that we can blend our digital object accordingly so that it will look natural, natural overlay on top of the real scene. We can present the information the way we want, like how much informative it should be, and based on that we can create our visual overlay on top of it. So it should be aesthetically looking. It should look like a blending with the natural object, so that it should not feel weird, right? Like it should not look artificial. So that's the main aim we have it in mind. And also, what are the markers or features we should take into account to blend our image? So that also we need to consider when we overlay some content on the virtual scene. I mean, on the real scene, virtual content on the real scene. This is one of the early intervention of AR application where the information manual is shown, like how the printer maintenance should be done. So there's the guidance given, overlay is given for industrial maintenance. That's the first applications, one of the first applications of the AR overlay there. So coming to the medical AR, we have early prototype in the 1994 where the womb, internal womb is overlaid digitally on top of the patient. So this we are showing it as example, but it has its own multiple challenges. Like we have to create accurate registration of the deformable tissues. Like here we don't have much features around. So those deformable object shape need to be considered to properly overlay our digital content on top of it. So, this gives a possible advancements, like how to take care of all these conditions to properly overlay, accurately overlay the digital content on top of the real information. Okay, so I hope this gave you some basic foundations on AR VR. With this, I open this for the discussion. If there are any discussions, I'm happy to take.
Dr. Praveen, thank you so much for your excellent talk on the
Yes, sir. Thank you, sir.
Systems like AR, VR. Yeah, thank you. I invite some questions from audience, if there is any. Audience can unmute and ask, please.
Sir, is there a possibility of sense of smell to be included? Because it's new to me, I don't know.
Yes, ma'am. So there is like electronic sensors, how to simulate it, olfactory information, how to digitally project that information to the user. That's also one field of research, ma'am. So along with the haptics, we also have the olfactory sensation stimulus, how to stimulate those stimulus to the user digitally. So that's also a field of research now.
Okay, sir. Thank you, sir.
Any other questions? Participants, any more questions, please ask. The feedback link for the session 4 is now posted in the chat box. I request all the participants to kindly fill it up. Dr. Praveen, it looks like there are no more questions. I think I thank you for your wonderful talk on this topic of AR/VR. Thank you so much.
Sure, sir. Thank you. Thanks for the invitation.